Hello, dear students. In today's class, we will have discussion about AODV protocol. AODV stands for Ad Hoc On Demand Distance Vector Routing Protocol. Before this lecture, we had discussion about DSR, that was Dynamic Source Routing Protocol, and as you know, that there the complete route was defined by the sender node and is added inside the header of a packet. So therefore, for large network, there will be a large header, and sometime these large header can degrade the overall performance of a network. It can create some extra delay as well as bring too much traffic on the network, which can result in a congestion or sometime even a blockage of certain network devices. Therefore, it is important or it is necessary that we should reduce the size of these header packet. Now moving toward AODV, that as compared to DSR protocol, AODV actually attempt to improve these issues of DSR protocol. Therefore, instead of providing the complete route from the source side, AODV try to maintain a routing table at the node so that data packet don't have too much route information from source to destination. AODV retain the desirable feature of a DSR protocol, and that's why it maintains some information on every node, which helps these nodes to decide about the next route or next node. So now moving toward AODV protocol. In AODV, there is a route request which is forwarded in the same pattern as we discussed in DSR protocol. When a node rebroadcasts a route request, it set up a reverse path pointing toward the source as well, that from which node he has received this data and to whom he is actually forwarding this data. So there is a maintenance of a reverse path from that particular node. One more important thing, as we discussed, that in AODV protocol, we assume that the links are bidirectional. So it means that you can communicate in both sides on the same link. When the intended destination receive the route request inside the network, it reply back to the sender or to the source node. So the route reply will travel along the reverse path that was maintained on each node inside that network, and it will be delivered to the source node. So the same reverse path which was maintained on the nodes while they receive a packet from any node, then onward forwarded to the next node, is used in reverse to reply back to the sender node. And this is the mechanism that sender node or source node actually came to know about the destination node. So which route should be followed to deliver the data, sender get the information about that. But instead of putting the complete track or the complete route in its header, it only maintain or keep the next node information in its header. Now moving toward this example, here we are still taking the same network topology which was discussed earlier in DSR protocol and other protocol. So here the node S sender will broadcast initially about the route request. So route request is broadcasted by node S, which was received by node B, C, and E in the surrounding or in the neighborhood. Then onward, B, C, and E will forward that packet to their neighbors. And you can see that BC also transfer this packet to node S, but A's node S already have this packet, or even it was initiated by node S, therefore he will not process it. Now F, G, A and H will receive the packet, they will process it, and it will be forwarded to the next new nodes. So here you can see that node C receive root request from G and H, but it doesn't forward it again because node C has already forwarded the route request. And similarly, you can see there is no node onward from A and H, so therefore the packet will be stopped over there, but we have nodes on the other side from J, K, therefore the process will continue onward from J and K. So the J and K, while receiving the packet, will be forwarded to their neighborhood. F already processed this route request, while M and D haven't processed this request, therefore they will process it, and M will forward it to the next node, this is L, while D is the desired destination, therefore D will not process this packet. So as you can see, node D doesn't forward this route request because node D is the intended destination or target node for this route request, while M forwarded to L and then L send it back, and then the process actually stopped over there. Now you can see as the D receive the route request from node S. Now it is responsibility of node D to prepare the route reply and then follow the same path to deliver the route reply to node S, which is the source node. So here you can see the red link represent the path that is taken by route reply to deliver data or information to source node. Now route reply in AODV is very important, and it is responsibility of the intermediate node that it may send a route reply provided that it knows a more recent path than the one previously known to the sender node. And as you know that how we can compare the old or the new packet. For this purpose, a destination sequence number is used, and as much the destination sequence number is higher, it means that this packet or this frame is more recent. So we should update or we should accept those packets in which the destination sequence number is higher. To determine whether the path known is an intermediate node, is more recent, or it's an outdated or older one, destination sequence number is used. And that's why I told you that sometime you may receive multiple packets at the same time, but you would not be able to, let me explain it here on the whiteboard. For example, this is a node, and this node receive these two packets or route reply, in which one destination sequence number is 12, in another destination sequence number is 23. So as you know, 23 is higher. This is the destination sequence number. So as the destination sequence number is this packet is higher, therefore we will consider that this data is more fresh, more updated than the last one. So it is more updated, therefore the node will actually accept the sequence number 2 and will leave the other one. So now you can see that the route request by node S for a destination is assigned a higher sequence number, and therefore an intermediate node which knows a route but with a smaller sequence number cannot send the route reply. So the destination sequence number, as we discussed on the whiteboard, for 23 will be accepted because it has higher number, while the other one which have 12, which is low, and as compared to 23, it is outdated information, will be discarded. So Here you can see in this diagram that the forward path that is used by the AODV protocol for data delivery. So the forward link are set up when root reply travel along the reverse path. Once the root reply is received, then onward the same path will be used by the sender to deliver its data. And therefore, in this diagram, you can see that node has sent its data to E forwarded to F to J, and J forwarded to D node. And therefore, the D node received data from source S. Routing table entries are used to forward the data packet, as we already discussed that there is a local table or local information maintained at each node, which actually helps them that which node should be the next. So therefore, route is not completely included in the packet header, but you just forward that packet to the next node, which is defined inside that route. Sometimes there may be a timeout, which results that either a path is used or a path is not used for longer period of time. A routing table entry maintaining a reverse path is purged after a timeout interval, and therefore the timeout should be long enough to allow route reply to come back. So therefore, it is important that the path stored in the table should be updated frequently. A routing table entry maintaining a reverse path is purged. Therefore, we have some timeout, and this timeout is most probably uh, equal to the RTT time. For example, if we have a sender and a receiver here in a network, and we send the data over here in 5 minutes, and then onward it moves back in 5 minutes. So therefore the time RTT over here, that is the round trip time, is 10 minutes. So in this situation, the time for expiry of a route should be at least more than this. As you can see here in this slide, a routing table entry maintaining the forward path is purged if not used for an active route time interval. For example, if you are not using this route for longer period, then it should be deleted from the table. If no data is being sent using a particular routing table entry, that entry will be deleted from the routing table, even if the route may actually still is valid. So there is some lifetime of every route, and after that, the entry will be deleted from the routing table. And that is also necessary to keep the routing table updated, as well as to add more fresh routes toward destination node. There is another important point, that is the link failure. Sometimes there may be the possibility of a link failure or a node failure that comes inside the route toward destination site. Therefore, when a neighbor of node X is considered active for a routing table entry, if the neighbor sent a packet within the active route timeout interval. So we can consider a node as an active node if it is participating properly and sending or sharing beacon messages about its status, that he is alive or he is available. When the next hop link in a routing table entry breaks, all active neighbors are informed. Whenever the next hop link in a routing table entry goes down, then it is responsibility of the node that it should inform its neighborhood node. And then I'll also start the other options for route discovery, or some other option for data discovery toward the destination node. Therefore, the link failure is propagated by means of a route error message, which is another type of packet, designed by that particular node, just like route request and route reply. So where the node or the link failure takes place, that is responsibility of the node which is directly connected to that link which is no more available to create or to design this packet and share it with the neighborhood node, which also update the destination sequence number. And as we discussed that it was earlier 23, 24, 25. So the packet with the root error information will be updated accordingly, and a higher sequence number will be assigned to that. Now, in root error, let's consider if we have different types of nodes, for example, a node X, which is unable to forward a packet P from node S to node D via a link X and Y, then it will generate the root error message. Node X increment the destination sequence number for node D cached at node X, and this incremented sequence number N is included in the route error. For example, if there is a route error, then it will be increased and it will be shared with the neighborhood node. When node S receive the root error, it initiate a new route discovery for D using destination sequence number at least as large as N. So the destination sequence number will be increased, and the main reason behind that is that every node receiving the route error message or packet should know that this is more fresh or more updated information. Therefore, they should give priority to this packet and updates their routing table accordingly that this link is no more available. Here you can have a look to the destination sequence number. When node D receives the route request with destination sequence number N, node D will set its sequence number to N unless it is already larger than N. So node D will forward it to the other nodes, and therefore node D sets its destination sequence number is higher as the root error was. And for other packets that will be created or that will be designed by these nodes will definitely have the higher sequence number. We can detect the link failure with the help of hello messages, in which the neighboring nodes periodically exchange hello messages or hello packets with one another. For example, if hello message is not received from a node in the neighborhood for longer period of time, then it gives us an indication that the link is failed or the node is failed, and it is not possible to forward your information or data through that link. Alternatively, we also have some MAC level acknowledgement which can help us about the link failure, based on which we can decide, we can design the packet of root error with higher sequence number and share it with the other neighbor nodes. Now, sequence number is very important, and it also helps us to avoid routing loops, as we have discussion earlier about these routing loops as well, that it is important to give sequence number so the nodes should be able to decide either they should accept information within this packet or they should drop it. So therefore, to avoid using old or broken route, and to determine that which information or which route data is more updated, we should use the sequence number. For example, in this topology, you can see we have 5 nodes A, B, C, D, and E. There is possibility of route error. For example, if there is no sequence number inside a packet. Assume that node A doesn't know about the failure of this link between C and D. And you can also see over here that node C and D has a connectivity with one another, but unfortunately that was down. that was failed. Therefore, it is responsibility of node C to inform. Let me share on the whiteboard over here. For example, if there is link failure of node C and D, then responsibility of node C is to design root error packet, then share with all neighbors, root error shared with all neighbors, 1, 2, and the third one is to find an alternative route, to find an alternative path or alternative route. So these are the responsibility of node C in the same topology as well. But unfortunately, the message shared by node C was not received by B and A or E, it was dropped. Therefore, when he started the third activity to find a route to node D, B and A, these nodes have older information in their memory or in their tables. Therefore, when C performed the route discovery for node D, node A received the route request through path C, E, and A. So A received a route request from node C about node D. As the root error packet was not received by node A, therefore it responds back with the older information. And now you can see that node A will reply since A knows a route to D via node B. So node A replied to E that I can provide access through node B, then C, and then D. So that results in a loop. For instance, the loop will be started from C, then move to E, then A, then B, and then will come back to C. So the packet will revolve inside this network for a longer time. Now here you can see that the loop is created, and that was because of the route error packet that was broadcasted by node C, but it was not received by node A. So therefore, there is a loop inside this network, and there is no connectivity with node D, but still all these nodes consider that they are forwarding data for node D. Now we will discuss the next protocol, that is TORA, temporarily ordered routing algorithm. So in TORA protocol, the source actually broadcasts the route request to the destination, as we all also seen in DSR protocol and AODV protocol. The destination will set its height to 0 and transmit a route reply packet. So therefore, each node along the way to the source increase its height by 1 and rebroadcast the route reply packet with its updated height. So it will start from 0 and then will move onward toward source. Here is the route request. You can see node S broadcast a route request that is received by B and A. B and A again broadcast their route request that is received by E, C, and G. G, C, and E again broadcast that is received by F and D nodes. Now you can see that as node D received the route request, it started to design the route reply. And as per this TORA protocol, it first select its height to 0 and then onward forward it toward the neighborhood node from which the route request was received. So the route request for received from E and F. Therefore, they are at height 1, then height 2, C and G and B. They are not directly connected with node D, and then onward we have node A, which is on height 3, while on the other side, sender S by itself is on height 3. So the route maintenance in this protocol Torah is totally based on triggered updates. When the last link toward destination is lost, then automatically it will start its height adjustment accordingly, and will propagate these information to all other nodes inside the network. Once the links are reversed to reflect the change, the route deletion is flooded to delete the invalid route. For example, once they have checked or they have exploited all the possible solution, then that couldn't find the possibility to connect with the destination node, then they will automatically delete this route from their routing table. Torah protocol actually modify the partial link reversal method to be able to detect partition. When a partition is detected, all nodes in the partition are informed and the link reversal in that partition is ceased. So here in this topology, you can see we have 6 nodes A, B, C, D, E, and F, where D is for destination D. Now the link between A and E is failed, and over here is per Torah protocol. We will use the modified partial link reversal method, in which we will exploit all the possibility that either there is any option through any other node that we can access the node E, D, or F. So here you can see with this possibility, first node A was checked. Node A has no outgoing link toward E. Then onward, we have checked node B. Node B has no outgoing link toward destination node E. And then onward for C, node C has no outgoing link. All its neighbor have reverse link previously, but now they don't have. And here you can see that we just reverse the links toward every node just to check that either they have any possibility by requesting them to get access or provide access to the desired destination node. And same here with the C, we are requesting node C to look all the possibilities that either it can provide any access to the destination or desired destination node. So as we have checked all the possibility in this part of the network, node A and B and C have no updates or no information or no connectivity with node D. Therefore, we will decide that the node E is partitioned from this network. Node B now has no outgoing link toward any other node, and we have checked it from all sides. Node A also received the reflection from its neighbor. Node A also determined that it is partitioning from node D. So therefore, after looking all the possibilities, we detect the partition of node A from node E. So therefore, node A send a clear message that purge all directed link in that partition. So node A actually update the information inside the memories of node B and C. And therefore, node B and C will not probably send any packet for node E to node A, which was earlier sent to node A because node A has a route or path to node D. So if we can have a look, this Torah protocol improves the partial link reversal method by detecting the partition and stopping non-productive link reversal. It also provides some sort of um, linkages or routes that was not the shortest. Another important thing is the directed acyclic graph, which provide the ability to send packet to a given destination. Now, it is beneficial when many hosts want to communicate with a single destination. So therefore, Tora protocol actually helps us a lot by first exploiting all the possibilities that we can share our information, our data with our desired destination. And then, for example, if after exploiting all these possibility, we couldn't find any link, any route toward the desired destination, we simply ask all of them to update their routes and delete those entries for the packets. So far, we have discussed about the homogeneous networks in which all these nodes have identical responsibility. Some schemes propose giving special responsibilities such as cluster head, such as a group leader, such as forwarding node based on their position and based on their uh, characteristic. But most of the characteristic of these nodes are same. Therefore, we were unable to decide some extra things or some extra possibility. But if you can see, we assign extra responsibilities to those nodes which have a good placement based on their position. So therefore, even if all nodes are physically identical with respect to their processing power, with respect to their transmission power, with respect to their memory, still we have this possibility that we can assign them a major role. For example, let me explain it here a little bit. For example, this is a homogeneous network in which all nodes are identical. They have same transmission power, they have same reception power, they have same memory, they have same computational or CPU power, and they also have the same battery. So they all are actually equal with respect to their characteristic. But there is still one thing that is the position of this node. The position of a node is not same based on which we can decide a cluster head or a group leader here, or as we have decided the forwarding node in our last example. So for example, if out of all these nodes, we want to decide a group leader, so this node can have the possibility to become the cluster head or a group leader. And this is not based on the characteristics such as resources available, but this is based on his position. And position is very important here because it can provide access to all these nodes from here at the same time. So this is the only criteria or characteristic based on which we can decide that this can be the cluster head. So I hope in identical network we can still assign some additional responsibilities, some special tasks to these nodes based on their position and not based on their characteristic because our resources, because most of them are same. So this is all about our today's lecture. And if you have any question, you can ask. Thank you so much.